Hello everyone, welcome to eSpace for a new lecture on sequence circuit analysis and synthesis. This is part 6. I am Chandla Chandran, MTech graduate from IIC Bangalore, senior engineer, now working as a senior engineer at Keltron. So in this lecture, we'll be talking about hazards, basically hazards in combinational circuit, types of hazards, hazard-free realization, that means how to design a hazard-free circuit, and hazards in sequential circuit and implementation with SR latches without hazard. Okay. So first, let us see what is hazard. What are hazard? Hazards are unwanted switch and transients that may appear at the output of a circuit because of different paths exhibit different propagation delays. That means suppose there is a combination circuit and there are many input variables and one output variable, and suppose for example when a single input variable changes from 0 to 1, then the output, suppose for example if it should stay at 1, it goes to logic 0 and then come back for a small amount of time, and this hazard is called static 1 hazard. That we'll be discussing we'll be discussing it later. And then hazards occur in combinational circuit where they may cause a temporary false output. When this condition occurs in, so this is our interest, when this condition occurs in asynchronous sequence circuit, it may result in a transition to a wrong stable state. That means the circuit totally fails there. So we will be seeing how to design without these hazards, how to design circuits without these hazards, and therefore steps should be taken to eliminate their effect. So we'll be seeing that in the coming lectures. So there are 4 types of hazards. One is static 1 hazard, which happens in combination circuit. Static 0 hazard happens in combination circuit, and dynamic hazard also happens in combination circuit. And these three combined, it can happens also in a asynchronous sequence circuit. And then the fourth one is essential hazard, that happens in asynchronous sequence circuit only. So first we will see what is static 1 hazard. So when a single variable change, it produces a momentary output change when no output change should occur. Actually, what the function says, it should remain at the state 1. That is, you can see here what the function says. That is, the circuit function says it should remain at state 1 or logic 1. The output should remain at logic 1. But when a single input changes from 0 to 1 or 1 to 0, then this output variable goes to 0 and then comes back for a small amount of time. So, and like this switching transition is called static 1 hazard. That is where it should stay at 1, then it goes to 0 and come back. Like this hazards are called static 1 hazard. So this type of hazard occur when there is a change in single input variable and where the function says the output should stay in 1, but due to different delay in different paths, that is because of the circuit architecture, because of the different delays in different paths, the output momentarily goes to 0 and comes back. That is static 1. So let us understand through an example. Suppose these are the input variables x1, x2, x3, and this is a changing variable, that is x2, and let us assume that x1 and x3 is remaining at 1. So this is x2 bar, this is x2 bar, x3, x1, x2, and this type of static 1 hazard happens in like this and or circuit, that is sum of product term circuit. Okay, so let us see here. This is x2, it is changing from 1 to 0. x1 and x3, as I have told, it is remaining at 1. Only x2 changes from 1 to 0. So this is the delay of this gate. Because of the delay, this is the x2 bar. It is changing from 0 to 1. See, this is a delay. And x1, x2, there is only the same delay as x2 bar. See, you can see this x1, x2 come here. Then x2 bar, x3, that is, it is a delay added to inverter. That is, it gives a 2-level delay. That is 2 gate delay. That is x2 bar, x3 is shown here. See, it's a delay here. So, and y is the OR combination of x2 bar and x1, x2. So this is the OR combination. So you can see this one here. So this is both are going 0. So there is a small space here where the output can go to 0. That is shown here. See here, this output goes to 0 because of this unequal delay in the circuit. So you can see this is the static 1 hazard where the output should remain at 1. It goes to 0 and come back. So that is called static 1 hazard. So how to eliminate static 1 hazard? So let us see the Boolean function of the circuit and its K-map. So this is the function y is equal to x1 x2 plus x2 bar x3. So this is the K-map for that. See, this is x2 bar x3 and x1 x2. So from this K-map only we have derived this function and we are seeing the earlier circuit. But what happens is when it switch over from one prime implicant to another, there is a 0. So the technique used to remove this hazard is group this redundant function, this redundant implicant. That is, we should add a extra AND gate combining these two 1. Okay. So let us see that. So this is, we are combining these and we are providing an extra OR gate, extra AND gate. That is, this is the function, the expression, the way the implicant for this one is x1 x3. Okay. So therefore for hazard free operation, this is x1 x2 plus x2 bar x3 plus x1 x3. Okay. So we are adding an extra gate, extra AND gate here with function x1 x3, and we are making a three input OR gate. So even if there is a different delay, this x1 x3 remains as 1 and output y stays at 1 without going to 0 and come back. So we have made a static round hazard free circuit. Okay. Next is static 0 hazard. When when a single variable changes, it produces a momentary output change when no output change to toggle. It's the same theory as static 1, but here the polarity is changed, the logic is changed. It is an inversion of the static 1 hazard. Okay. So where the output should remain at 0, it goes to logic 1 and then come back when any of the input variable changes from 0 to 1. Okay. So this type of hazard occur when there is a change in single input variable and where the function should stay, when function says the output should stay in 0, but due to different delay in different paths, the output momentarily goes to 1 and come back. So here, see, we have like this 1 pulse. Okay. That is static 0 hazard. Then let us understand through an example. These are x1, x2, x3, x4, 4 variables, and where x1, x3, x4 remains at 0, only x2 changes from 0 to 1. So let us see here the waveforms. The functions are x2 bar plus x3 plus x4. Here it is a product of sum. Okay, product of sum expression, and this is x2 bar plus x3 plus x4, then x1 plus x2, then x1 bar plus x3 bar. So let us see the K-map for this. So these are the waveforms. When x2 changes from 0 to 1, see x2 bar changes from 1 to 0. This is the single delay of the inverter. And x1 max x2, there is only one level gate. So there is only a single gate delay. See x1 plus x2. And this is x2 bar plus x3 plus x4. See here, there is two gate delay. That is one is that of inverter, and then there is an OR gate. So it delay, there's a 2 gate delay here, 2 level delay. So it comes like this. So, and y is a AND operation of these 3 variables. Okay. So these 3 variables, that is x1 plus x2, x1 bar plus that is at 1. So there is no issue there. This is only changing. So this is an y is the AND operation of these 2 1. So you can see here, it is coming, these 2 AND operation. See, when these 2 AND operations coming, there's a little space here to make a 1 at the output. So that is shown here. See here. So this is 1 here. The AND operation of x1 and x1 plus x2 and x2 bar plus x3 plus x4 here it is going as 1. Okay, so there is a momentary false output coming at the false change coming at the output, that is at 1, where it should stay at 1 all the time, stay at 0 at all the time. It is going to 1 and coming back. So that is called static zero hazard. So let us see the Boolean function of the circuit and its K map. This time it is product of sum. See here, this is the expression, product of sum expression. So here we have to group in the K map, we have to group zeros. So let us see which are the max terms. So these are the max terms of this expression, that is 0, 1, 2, 3, 4, A, B, C, E, F. We can work it out and see here. These are the max terms. So this is the K map for that. This is the first function, second function, third function. So what here again, there is a redundancy here where we usually avoid for the design of the circuit, but for a hazard free realization we should include that redundant gate also. Okay, so here we are grouping this, then we are grouping this, and here finally we are grouping this. So we are adding 3 extra gate to the circuit, extra OR gate to the circuit. So here it is x2 plus x3 bar, x1 plus x3 plus x4, x1 bar plus x2 bar plus x4. These are 3 gates added for redundant. These 3 redundant gates are added. That is extra gates are added for a hazard free realization. So here where it should remain at 0, it will where the output should remain at 0. It will be this term will be providing it at 0. Okay. Next is dynamic hazard. This type of hazard causes the output to change 3 or more times when it should go from 1 to 0 or from 0 to 1. So where the actually the function what the theory says, it should go from logic 1 to logic 0. See here, it goes to 0, then goes to 1, and then come back. Again, this can also go up and come back. Then it is called a dynamic hazard. That is, there is some, just like some oscillations. Okay, there is some uncertainty for the output. Okay, the removal of static. So to remove dynamic hazard, we usually remove all other hazard. That means static zero and static hazard is removed from a circuit. Then it does not have any dynamic hazards. That is, the removal of static one hazard guarantees that no static zero hazards or dynamic hazards will be occurring. So let us understand through example. This is a function here. Okay, so this is a OR gate. These are the variables x1, x2, x3, x4, where x4 is 1, x3 is 0, and x2 changes from 0 to 1, and x1 is 0. So this is slow. This is a slow gate where there is a more delay than other gates, and this is another gate. It's a maximum delay, and this is the most slowest gate, and it has the maximum propagation delay other than all other gates. Okay, so let us see the waveforms. This is x2 here. See, x2 changes from 0 to 1. See, it changes to 0 to 1, and x2 bar after one inverter delay, it is going from 1 to 0. Then x1 plus x2, x1 is at 0 and x2. So the logic output of this is like this, but it gives a more delay than inverter. So it is remaining like this. It is a slow gate. That is, so it is giving more delay than other gate. Then x2 bar plus x3, that is this one. It is a more slower gate. Then it is giving more delay than this gate. This is the maximum delay gate. Okay. So this is going from x2 bar plus x3. So this is giving more delay. We can see here. And this is Q. Q is an AND operation of these 3 variables. Okay. See, this is the delay. After this delay, it is coming like this. Q, and P is a AND operation of these 2 variables. See here, P is the AND operation of x1 plus x2 and x2 bar plus x3. See here. x2 x1 plus x2 and x2 plus x3, the AND operation of these two. So after a certain delay, it will be going like this. You can see here, you can imagine. Okay, so finally the output y is the OR operation of P and Q. Okay, OR operation of this. So what is the OR operation of this? Here we will get a 1. Here both are 0. So it is going to 0. And here it is 1 and 0. So it will 1 and 0. And finally it is both are 0. So everything will be 0 at the final state. Okay, final time. Okay. So what we can see here, it is actually because of this change x2 going from 0 to 1, it should change from 1 to 0 without this transition. Okay, so this is called the dynamic hazard. So how to remove hazard in dynamic hazard means if you remove static 1 and static 0 hazard, then the dynamic hazard will be automatically removed. Okay, you can see here this is actually a static 0 hazard. If you remove this static 0 hazard, you can remove this dynamic hazard also. Okay. Next, hazards in sequential circuit. So in normal combinational circuit associated with synchronous sequence circuit, it is not a big concern because of the presence of clock. So in a synchronous sequence circuit, the output value changes only at the transition of clock, and at that time there's a low probability that any of the input changes. So this will be not much of a concern. Okay, but if a momentary signal is fed back in the asynchronous sequence circuit, it may go to a wrong stable state. Okay, so let us understand through an example. This is an example. There's a feedback here. This is the excitation state, and this is the output y here, and the function is x1 x2 plus x2 bar small y. Okay, and there are 3 gates here. And there are 3 gate delay. Okay, 3 level gate, 3 level equation, 3 level architecture. Okay, so if the circuit is in total stable state, y x1 x2 equal to 1 1 1. So by looking at the transition table, we can say that, see here, there is 1 2 3 4 5 6 stable states, and 3 are at 0. Sorry, yes, 4 are at 0, and then 1 2 ones are at 2. There are 2 at 1 stable state. Okay, so if the circuit is in total stable state, y x1 x2 1 1 1, that is here. Suppose if the state is the circuit is in state this. Okay, this state, that is 1 1 1, that is y, where x1 x2 is 1, and then y is also equal to 1. So and then an input x2 changes from 1 to 0, that is it changes from this x1 x2 changes from 1 1 to 1 0. So there are 2 such stable state, but according to the equation, see here, according to the map, this when the input changes from x2 changes from 1 to 0, it is at stable state 1, the output is 1, and that is fed back to the input gate. You can see here, see, this is at 1 and this is fed back to gate number 2. So when the input, that is the x2 changes from 1 to 0, because of here it is 1, it should remain at this state, that is it should go at this state, that is 1 1 0. Then the next state, see here, then the next stable state should be 1 1 0. However, because of the hazard output, suppose when changing from 1, this should remain at 1. Suppose there is a static 1 hazard. So as we have seen earlier, the output goes to 0 momentarily. So the output may go to 0 momentarily when this false signal is fed back to the gate. So suppose this 0 is fed back here, then it gives 0 here. So the output y becomes 0. Okay. So when this false signal is fed back to the gate 2, before the output of the inverter goes to 1, the output of the gate 2 will remain at 0, and the circuit will go to stable state 0 1 0. So instead of 1 1 0, it goes to 0 1 0. So see, from seeing the map here, see here, this is the stable state here. This is at 1 1. Okay, we have combination here. These two are implicant. So how to remove this? the solution is to provide a redundant gate as done in combination circuit. So this will group here. These two implicants will be grouping. That is a redundant. Will be putting an extra gate. That is extra redundant gate here to remove the hazard occurring in this asynchronous sequence circuit. So the solution is to provide a redundant gate as done in combination circuit. So this will solve the problem by eliminating the momentary false signal generating in the circuit. So that is the solution. Then you can just work it out. I am not showing here. Then implementation with SR latches. So another way to avoid static hazard in asynchronous sequence circuits is to implement the circuit with SR latches. Why? Is because a momentary zero signal applied to a NOR latch or a 1 applied to a NAND latch. So there is no effect in the no effect in the latch, because suppose a momentary zero signal is applied to NOR latch means it will be remaining in the same state, and one applied to a NAND latch it will remain in the same state. So if we give this a hazardous circuit to a input to a latch, NOR latch or NAND latch, we'll be getting a hazard free asynchronous sequential circuit. Okay, if the output gate shown in previous hazard circuit examples is part of latch. So you have seen here, we have seen in the previous hazard circuits, the momentary one signal will have no effect on the output because a third input to the gate will come from the complementing side of the latch, that will be equal to 0, because there are Q and Q bar. Okay, suppose we are feeding a momentary one signal to the NAND latch, then there is a complemented output, that is Q bar is coming to the third input of this gate, and that will make it will be equal to 0 and thus maintain the output at 1. Okay, so let us understand through an example. So consider a NAND latch, SR latch with the Boolean function for S and R. S is equal to AB plus CD, R is equal to A bar C. Since this is a NAND latch, we must apply the complemented values to the input. So we have discussed earlier, for a NAND latch, it is the input is S bar, R bar. Okay, so S will be complementing that. So AB plus CD the whole bar equal to AB bar into CD bar, and R is equal to A bar C the whole bar. Okay, the Boolean function for output is then Q is equal to Q bar S the whole bar. So you will get here Q bar into AB bar into CD bar the whole bar. Okay, so this is a latch implementation. See here we have put that function S function and R function here. This is R, this is S. So and then combining these two gates, we can make this as a 3 input gate. Okay, and this you can 3 input, and this is function here. So in this circuit, this is a hazard free asynchronous circuit or hazard free asynchronous latch. Okay, hazard free asynchronous sequential circuit. So next one is essential hazard. I'm not going into deeply because it is a more advanced topic and it differs for different circuits, and in different circuit there are different parts, and that the condition differs for these many combinations. Okay, it occurs in asynchronous sequence circuit. It is caused by unequal delay along two or more paths that originate from the same input. Suppose there is single input and there are unequal delay along two or more paths, then there will be essential hazard. That is, it goes to a wrong stable state. Okay, because of these unequal delays. So this cannot be corrected by adding redundant gates as in static hazard. That is important point here. This cannot be corrected by adding redundant gates. Okay, as we have done in previous circuits. They can be corrected by adjusting the amount of delay in affected path. Okay, suppose there are more delay in one path and less delay in another path, we can make by giving more we can adjust the delay in the smaller delay circuit and equaling it to the bigger delay path. Okay, so to avoid essential hazards, each feedback loop must be handled with individual care to ensure that the delay in the feedback path is long enough compared to delay of other signals originate from the inputter. So making the feedback path, that is making the delay for same in for all the path will be we can tackle this essential hazard. Okay. So this problem is specialized as it depends on particular circuit. I have already told here, it depends on particular circuit and encounter in various paths. And for a particular circuit, it will be different in different paths for different paths and different input combinations. Okay. So that's it. Please like and share the video, subscribe the channel, and you can send the comments to you can, if you have doubts, you can mail me to chanch484 at gmail.com, or you can put at the comment section. Okay. Thank you.